Hello, myself Anirban Vishwas. Today I am going to explain chapter 5 of the subject Digital Circuit Design using Verilog. In this chapter, we are going to quickly see about the gate level modeling. The built-in primitive gates. The following built-in primitive gates are available in Verilog STL. Multiple in-gate input gates AND, NAND, OR, NOR, SOR, XNOR, multiple output gates, BAF, NOT, tri-state gates, BAF if 0, BAF if 1, not if 0, not if 1, pull gates, pull up, pull down, MOS switches, CMOS, NMOS, PMOS, RCMOS, RNMOS, RPMOS, bidirectional switches, TRAN if 0, TRAN if 1, I, TRAN if 0, I-TRAN if 1. Now we come to multiple input gates. The multiple input gates are AND, NAND, NOR, OR, SOR, XNOR. These logic gates have only one input and one or more inputs. Here is the syntax of a multiple input gate. Multiple input gate, instance name and out- output and all the inputs that we will be using. Here are the few examples of multiple input gate examples. For instance, this one here out one is the output, int one and int two is the input of AND gate A1. Here is shown the table of AND, NAND, and OR, NOR, SOR, etc. Let me explain one table of the AND gate where these are the operands and these are the results from zeros 0 0 0 0 1 0 x 0 0 z 0 1 0 1 0 1 x x 1 z x and so on. Similarly, all these tables are structured in a similar way. Multiple output gates. The multiple output gates are PUF and NOT. These gates have only one input and one or more outputs. The basic syntax for this gate is multiple output gate type, instance name, output 1, output 2, output. There are multiple number of outputs that you can give on a single input. Already discussed definition. Here are some examples of multiple output gates. In this case, for instance, this is the input A, this is a NOT gate, and there are n number of outputs. Here are some examples: BUF, P1, F0, F, pen 1, pen 2, clock. The clock is the input. Here is the truth table for this gates: BUF, BUF gate and NOT gate. This is the input, and this is the output. Tri-state gates. The tri-state gates are BUF if 0, BUF if 1, NOT if 0, NOT if 1. These gates model three-state drivers. These gates have one input, one data input, and one control input. The basic syntax of the tri-state gate is the name: output A, input B, control C. The first terminal output A is output, the second terminal is the data input, the control input is the control C. Figure 5. In this figure, four basic examples of tri-state gates are given. Notif 1, profit 1, notif 0, profit 0. The input in notif 1, input B is given, output and the control C is given. Say, depending on the control input, the output can be driven to the high impedance step, that is two values Z. For a profit 0 gate, profit 0 gate, the output is Z. If control is 1, else the data is transferred to output. For a profit 1 gate, the output is Z if the control is 0. Not if 0 gate, the output is Z if the control is 1, else output is the invert of the invert in data value. For not if 1 gate, output is at Z if control is at 0. Few examples are profit 1, BF1, reverse when data strong. This is the table of the tri-state gates: profit 0, profit 1, notif 0, notif 1. And this is the data value, and this is the control value, and these are the result. All the four are designed in a similar structure. Next we come to the pull gates. The basic pull gates are pull up and pull down. These gates have only one output with no inputs. A pull up gate places a 1 on its input, a pull down gate places a 0 on its output. A gate instance name is of the compound gate instance name and output name. For example, we see an example pull up pub, PWRP. Pub is the instance name and PWR is the output. This pull up gate has instance name pub with output PWR. Type to 1. Let us see the MOS switches. The basic MOS switches are CMOS, PMOS, NMOS, RCMOS, RPMOS, RNMOS. These gates model unidirectional switches, that is, data flows from input to output, and the data flow can be turned off by appropriately setting the control inputs. The PMOS, that is P-type MOS transistor, NMOS, that is N-type MOS transistor, RNMOS, where the R transfer resistive and RPMOS switches have one output and one control input. The basic syntax for the MOS switches are gate type, instance name, output A, input B, control C. If control, here we can see the figure of NMOS switch and PMOS switch. So if control is 0 for NMOS, then RNMOS switches, and 1 for PMOS and RPMOS switches, the switch is turned off. That is, output has value 0. If control is 1, data at input passes to output. The resistive switches RNMOS and RF have higher impedance between the input and the output terminal as compared to the non-resistive switches NMOS and PMOS. Thus, a reduction in the strength occurs for resistive switches. The truth table for these switches, as you can see here, PMOS, PMOS, NMOS, RMOS. So this is the data value, this is the control. This is the result of the time the control value. These two are structured in a similar way. The CMOS, complementary MOS and RCMOS, resistive version of CMOS switches have one data output, one data input, and two control inputs. Syntax: this is RCMOS instance name, output A, input B, and control and P control. Here is the diagram of RCMOS switch. First terminal is the output, the second is the input, third is the N channel control input, and the fourth terminal is the P channel control input. A CMOS or CMOS switch behaves exactly like a combination of PMOS and an NMOS and RNMOS switch with common outputs and common inputs. Now let's see what are bidirectional switches. The bidirectional switches are TRAN, RTRAN, TRAN if 0, RTRAN if 0, TRAN if 1, RTRAN if 1. In this, data flows both ways and there is no delay when data propagates to the switches. The TRAN and RTRAN switches cannot be turned off. The basic syntax for TRAN and RTRAN are TRAN instance name signal A to signal B. The terminal list has only two terminals and data flows unconditionally both ways, that is, from signal A to signal B and vice versa. The syntax for instantiating the other bidirectional switches is gate type, instant name, signal A, signal B, control C. The first two terminals are the bidirectional terminals, that is, data flows from signal A to signal B and vice versa. The third terminal is the control signal. If control C is 1 for TANF 0 and RTANF 0 and 0 for TANF 1 and RTANF 1, the bidirectional data flow is disabled. For the resistive switches, that is RTAN and RTANF 0 and RTANF 1, the strength of the signal reduces when it passes through the switch. This will be further discussed and more briefly in chapter 10 later. Let us see what are the gate delays. The signal propagation delay from any gate input to the gate output can be specified using a gate delay. The gate delay can be specified in the gate instantaneous itself. The basic syntax for the gate delay is gate type delay, instance name, the terminal list. The delay specifies the gate delay, that is, propagation delay from any gate input to the output. When no gate delay is specified, the default delay is 0, as we have already discussed in earlier every chapters. The gate delay can be compromised to three values: rise delay, fall delay, turn off delay. Here is the table for these three type of delay: rise, fall, turn off. The 2x represents the transition to x delay. That cannot be explicitly specified but is determined by the other specified. When there is no delay, all the values are 0. When there is only one value, all the values are same. When there is two values d1 and d2, the rise delay will be d1, rise fall value will be d2, and turn off delay will be the minimum of d1 and d2. When there are three values of dA, dB, and dC, the rise value will be dA, fall value will be dB, turn off value will be dC, and the transition to x delay will be minimum of these three values. Note that all the values in the Verilog SDT model are expressed in terms of time units. The association of time units with actual time is done using the timescale compiler type. For example, here the gate delay is 0 since not N1 Q1. In here there is no delay. But in here NAND #6 here there are 6 nanoseconds of delay. The rise delay and the fall delay are both 6. Turn off delay doesn't apply to a NAND gate since the outer output never goes to the higher impedance. Let's now see the minimum type max delay form. A delay for a gate can be specified in the minimum type max form. Minimum, typical, the form is minimum, typical, maximum. The minimum, typical, and maximum below must be constant. Must be a constant expression. There is an example of a delay from instant gate instantaneous. Then 2 is to 6 to 4, 5 is to 6 is to 7. This is the minimum, typical, maximum. P out P1, P2. The selection of which delay to use is usually made as an option during a simulation run. For example, if maximum delay simulation is performed, a rise delay of 4 and a fall delay of 7 is used for the NAND gate instance. Array of instances. When repetitive instances are required, a range specification can operationally be specified in a gate instance. The basic syntax for the array of instances are get type delay, instance name, left bound to right bound, list of the terminal names. The left bound and the right bound values are any two constant expression. It is not necessary for to be greater than the right bound, and either of the bounds is not restricted. For example, here where is the gate type 3 is to 0. Now in again here the delay is 0 0. Similar here is an example of an in gate. Next we come across implicit nets. If a net is not declared in a Verilog SDL model, by default it is implicitly declared as a 1. However, the default net type compiler directive can be used to override the default net type. Use of the form default net type. For example, here is an example of the default net type 1. Just come across a simple example. Here is the gate level description to 4x1 multiplexer. Model length works 4x1. These are the output Z. And these are the inputs. Here it is described, specifically describe the output and the inputs. These are the AND gates. You can see in here T0, T0 AND gates. T0 T0 is the output, T0, SO bar, and SO bar are the inputs. Similarly, these four NOT gate, NOT gates, SO, this one, NOT gates, SO bar is the output, where SO is the input, and similarly the OR gate, where there is the final output, and T1, T2, and T3 are the inputs. So finally, we have to the LND. Similar example with a 2 to 4 decoder multiplexer model and model name decoder 2x4, where A, B, and enable are the inputs and Z is the output. Here it is mentioned input A, B, enable and the output, where Z is a 4-bit A 4-bit vector where A bar and B bar at the NOT gate having a delay of 1 and 2, V naught, A bar A, B bar B. And similarly, the NAND gates are described. 4 NAND gates Z0, Z1, Z2, Z3 with a delay of 4, 3. We come across another example of a master slave flip-flop example. The master slave did a flip-flop example module MSDI where DC are the input, Q and Q bar are the output, ANC Q and Q bar are the output, TLC are the input. The NAND gate are specified as this is expressed in a behavioral structure. So NOT gate and all the NAND gates are specified separately. And finally, and we come across another parity circuit module. A gate level module for a 9-bit parity generator. Here is the figure of the parity generator. Let us see how the coding part module. Then the module name parity 9-bit. The D is the input. Even or are the output. Input is a 9-bit vector. Since 0 to D0, D1, D2, D3, D4, D5, D6, D7, D8 are the input. Since it is described in a behavioral structure, all the XOR gates are specifically described in here. Finally, the NOT gate is also described and module. Thank you.